power limb up is, do they have a rotation axis, or sorry, improper rotation axis? But usually it's not necessary to go that extreme. That's just a couple of examples of some of the properties of molecules that we can deal with through these symmetry operations. What we really want to do is, rather than looking at individual symmetry operations in molecules, is look at something that somehow tells us what all of the symmetry operations are in a particular molecule. And for that, we have what are known as point groups. And these point groups describe the symmetry of the molecule in just one term. Okay? And then we can use that to establish the properties of a molecule as a whole. Okay? The point group denotes all of the symmetry elements in the molecule. Okay? It's not just looking at, does it have this particular element, or does it have that element? The point group describes all the symmetry. So the point groups are what are known as Schoenflies symbols, and they look like the C2B, TE, OH. These are point groups. Okay? The TD is actually describing a tetrahedral geometry. The OH is an octahedral geometry. And after you've worked through some of these, you'll see that some of them come up quite often. There are some that we regularly encounter, and you won't have to go through a lot of operations to establish that it has this particular point group assigned to that molecule. Some of the other, some of the other ones are a little more awkward, and you're going to have to go through a more detailed process to establish what the point group is. Okay, let me just try and illustrate a little bit of this. We've got the boron trifluoride, the molecule I've been using over and over again as an example, against ammonia. They have some similarities in their symmetry. The boron trifluoride has a threefold axis symmetry. It has a C3. The ammonia also has a threefold axis. It also has a C3. This is a trigonal planar molecule, which is nonpolar. The ammonia is trigonal pyramidal, and it is polar. And if we go through the operation of establishing what the point groups are, the boron trifluoride is something that is denoted D3H, and the point group for ammonia is C3B. We have different point groups, and the different point groups would actually tell us that they have different properties. So things like the polarity will be different in the different molecules, and we can see that when we just know what the point groups are. Okay, I'm getting a little ahead of myself here, but the idea is what we really want are these point groups. That's our objective. Get the point groups, and then we'll be able to use some other information that comes with them to establish all these other properties we want to look at. Now, I know this is small, and I doubt you can actually see it, but this is a table 6.2. Again, it's taken out of the course kit, and it summarizes some of the more common point groups. So it goes through, down here is our TE, a tetrahedral one for things like methane, for example. Octahedral, for an octahedral species here, like we have the sulfur but we get into some other common structures. Square planar, we've talked about before with splitting pattern. That's a D4H. And some of these, after you work through a few of the examples, you see that they're common ones that you'll jump to right away without going through a detailed determination of the point group. Okay. We don't want to look at all the symmetry elements of the point group. We want to identify the point group. Now, this is where I'm skipping a lot of math I'm just going to the point where what we do is establish, based on the symmetry of the molecule, what the point group is. And then there's something called the character table. And the character table is associated with a particular point group. And that character table is what you then use to establish the properties of the molecule. Okay? We'll look at those details later after I've taken some time to describe what the point groups are and how we determine those. So I just want to go through some of the more common ones so that you can identify them just simply by looking at it and say, oh yeah, that one is like this, and not have to go through a detailed determination. If we have a molecule, something like this, where we really have no symmetry at all. So we can think of this as, okay, we've got something, carbon atom with 4 different things around it. Okay, so it's going to be carbon. So here, just give the example, carbon with 4 different things around it. There's really no symmetry to it. That is denoted as C1, which is just equivalent to the identity element E. The point group is not E, it's C1. Okay, so that's one that basically doesn't have any symmetry to it whatsoever. We start getting into linear molecules, then we can get into some that are fairly easy to identify. We have a linear molecule that does not have a center of inversion. Okay, here got the setup as carbon monoxide, so we don't have something in the middle that we can perform inversion or reflection. Here, this is hydrogen cyanide. Again, we can't do a reflection or an inversion about that center. This is referred to as C infinity V. C infinity because along that axis, it's being drawn horizontal here, but the principal axis would actually be vertical. We could denote that as a C infinity axis because you can go through any angle or any fraction of an angle, and it doesn't change the molecule. Okay? So we don't really have a predefined angle of rotation. When we're actually rotating along the axis, nothing is changing. Okay? So the C infinity axis is only when we have this linear type of molecule where we can rotate about any angle we like. Okay? So when we have that as our principal axis, then we can also have a vertical plane. And that vertical plane, we can perform the reflection, an infinite number of vertical planes that you can perform reflection about, and it doesn't change the molecule. Okay? So these are going to be, pardon me, these are going to be heteronuclear diatomic molecules or polyatomic molecules. Hetero, they have to be different. Okay? We don't have something that is in the center serving as an inversion center.